Since the first days of the American automobile industry, Buick has been a leader in innovation and technology. The first overhead valve engine was patented by Buick in 1903. From then on, Buick vehicles were known for reliable, powerful engines and overall quality. In 1931, the first 8-cylinder Buick engines were introduced. They set new standards for quietness, reliability, and power throughout their operating range. In 1953, the first Buick V8 was introduced. At the time, it was one of the most powerful production engines built in America. In 1961, the first V6 engine used by Buick was introduced in the Skylark. This strong, reliable, and compact engine was the forerunner of other V6 engines to come. In 1978, the Regal became the first Buick with a turbocharged V6. There were many innovations used on the engine, including a knock sensor and electronic spark control. Still on the leading edge of technology in 1986, Buick brought the Intercooler from the racetrack to the turbocharged Regal. At 235 horsepower, the turbocharged V6 used in the Grand National is the most powerful production engine currently built in America. This engine comes standard with an intercooler and sequential fuel injection. Recently, an entirely new series of V6 engines designed specifically for front-wheel drive vehicles has been introduced. To bring you up to date on the latest engine changes, Buick Know-How presents Engine and Turbocharger Update. At the beginning of the 1985 model year, a completely new 3-liter V6 was introduced. Then at the beginning of the 1986 model year, 2 new 3.8-liter V6 engines, similar in design to the new 3-liter, were introduced. For the sake of clarity, the 3 new engines will be referred to as the new generation V6 engines. The traditional 3.8-liter V6 and 3.8-liter turbocharged V6 continue to be produced for rear-wheel drive cars. Although at first glance new generation engines may look similar to the traditional design V6, almost no parts are interchangeable. Many parts, including the cylinder heads, valve train, and front timing cover, are totally different. The block deck height on the new generation 3-liter V6 engine is 1¼ inches lower than all other V6 engines used by Buick. The new 3-liter V6 engine is referred to as the low-deck V6. The lower deck height causes changes in crankshaft, connecting rod, piston, push rod, and block design. Many parts of the 3-liter low-deck V6 are not compatible with the new generation 3.8-liter engines either. There are some easily recognizable differences that will allow you to quickly tell the difference between a new generation engine and a traditional V6 engine. The new generation engine uses acorn nuts in the center of the valve cover to retain the valve cover. Also, on the new generation V6, there is no opening in the timing cover for a fuel pump or distributor, as there is in the traditional V6 engine. The cylinder head and valve train on the 3-liter and 3.8-liter new generation V6 engines are totally new. The new valve train uses individual rocker arms, rocker arm bolts, and rocker arm pedestals. 3 of the rocker arm bolts have studs at the top which hold the valve covers in place. The traditional V6 engine uses a common rocker arm shaft for each head that all rocker arms pivot on. Pedestals for the rocker arm shaft are part of the cylinder head casting. To remove a single rocker arm, all rocker arms on that cylinder head must be removed as an assembly. All of the 3-liter and 3.8-liter new generation engines use a new oil pump referred to as a G-rotor oil pump. The oil pump is built into the timing chain cover and driven by the lower timing chain sprocket on the crankshaft nose. The G-rotor oil pump is a rotor-type pump similar in design to an automatic transmission oil pump. The main reason Buick designed this oil pump was to improve oil pressure at idle. All new generation engines produced after mid-year 1985 use a double flat drive for the inner pump gear. However, the early 1985 3-liter low-deck engine uses a spline drive inner pump gear. This design was changed at mid-model year 1985. The main parts of the G-rotor pump are the timing chain cover, lower timing chain sprocket, outer pump gear, inner pump gear, and pump cover. The pressure relief valve is also built into the timing chain cover. The early 1985 3-liter low-deck engine can be changed to use the double-flat inner pump gear rather than the spline drive, but many parts will have to be changed. Also, the spline drive system uses an aluminum seal between the timing chain sprocket and the crankshaft balancer. The arrow in the picture points to the seal. This must be discarded when changing drive systems. Parts are stocked for both type pumps, so there is no need to switch from one style pump to the other. The parts that would need to be changed are the crankshaft balancer, inner pump gear, lower timing chain sprocket, and crankshaft balancer washer and retaining bolt. The new generation 3-liter and the 3.8-liter V6 engines use a lip-type crankshaft seal in the timing chain cover. Traditional 3.8-liter V6 engines use a rope-type crankshaft seal in the timing chain cover. A new, improved type of head bolt called a tension-to-yield head bolt has recently been introduced. They are commonly referred to as torque-to-yield bolts in the field. This design provides more uniform clamping pressure on the head gasket. Improved types of head gaskets have also been introduced. The 3-liter low-deck engines have used torque-to-yield head bolts since their introduction in 1985. Then, at mid-year 1985, the 3.8-liter traditional design multi-port fuel injection V6 engine also started using torque-to-yield head bolts. Torque-to-yield head bolts were adopted across the board in all V6 engines used by Buick at the beginning of the 1986 model year. The 1985 torque-to-yield head bolts use a reduced shank design which cannot be reused. The 1986 and later torque-to-yield head bolts use a full shank design which can be reused. Torque-to-yield head bolts can be used with any gasket, but remember to use the torque-to-yield tightening process with these bolts. Notice that the full shank torque-to-yield head bolts in the middle appear to be very similar to the conventional head bolt on the far right. The difference is the conventional head bolts have a shallow hollow in their head, shown here by the arrow, whereas the torque-to-yield head bolts do not. The early 1985 3-liter low-deck V6 engines and some mid-year 1985 3.8-liter engines came equipped with spring steel head gaskets and torque-to-yield head bolts. Previous to this time, all V6 engines used by Buick came equipped with conventional head bolts and steel head gaskets. The spring steel head gasket in the center can be identified by the extra tab on it. Then, at the beginning of the 1986 model year, all V6 engines used by Buick adopted composite head gaskets. Because of the thicker head gasket, the block deck height was reduced 38 thousandths of an inch. All 1984 and 1985 engines may be upgraded with torque-to-yield head bolts and spring steel head gaskets. However, using steel or spring steel head gaskets on 1986 or 1987 engines designed for composite head gaskets is not recommended and will increase compression. The increased compression may cause pre-ignition or detonation, which will damage the engine. Also, using a composite head gasket on an engine that came equipped with a steel head gasket will reduce the compression ratio and the performance will suffer. The tightening procedure on torque-to-yield head bolts is different from the procedure used on conventional head bolts. It is very important that this procedure is followed whenever torque-to-yield bolts are used. The first step is to tighten all of the head bolts in sequence to 25 foot-pounds. The second step is to use the tightening sequence and tighten each bolt 90 degrees, which is 1/4 turn. Use a torque wrench to tighten the bolts so you do not tighten any bolt over 60 foot-pounds. The third step is to again tighten each bolt 90 degrees. Be careful not to tighten any bolt over 60 foot-pounds. It is extremely important that the correct procedure be used for each bolt. Failure to follow the correct procedure could result in broken head bolts, head gasket failure, and possible engine damage. The usage chart included in the Know-How Reference Manual tells which bolts and gaskets are used with which engine. It also contains the proper procedure for using torque-to-yield head bolts. If a question arises on which parts should be used in a 1985, 1986, or 1987 engine, the parts catalog should be the final authority. Beginning with its introduction in 1986, the new generation 3.8-liter sequential fuel injection engine with a number 3 VIN code is equipped with hydraulic roller lifters. All other V6 engines used by Buick have conventional hydraulic lifters. Now, let's discuss some rebuilding tips that you should be aware of. Several important parts of an engine, including the pistons, main bearing inserts, and rod bearing inserts, are precision fit for more exacting clearances. Other parts wear in when they are in use. Because of this, it is very important that certain parts, such as pistons, valve lifters, push rods, rocker arms, and valves, be returned to the same location in the engine they were removed from. Main bearings are precision fit parts. Original equipment manufactured bearings are supplied in 3 sizes: standard, 1/1000th of an inch oversize, and 2/1000ths of an inch oversize. It's possible to have all 3 size bearing inserts in the same engine. There are 2 methods for measuring bearing clearance. One method is to use a micrometer. The other method is to use plastic gauge. Most engine rebuilding technicians are familiar with both methods. Here are some tips for using plastic gauge. The first is, do not rotate the crankshaft with the plastic gauge between the journal and the bearing insert. If a main bearing is measured in the car, the crankshaft must be supported. If it is not, the weight of the crankshaft will compress the plastic gauge, giving a false reading. Taper can be checked with plastic gauge. To check taper, be certain the plastic gauge is stretched across the entire width of the journal. After torquing the cap, check the width of the plastic gauge on both ends. If the clearance on each end of the journal differs more than 1/1000th of an inch, the crankshaft will have to be either reground or replaced. If no taper is noted but the clearance is excessive, an oversized bearing will have to be installed. Also remember that bearing insert halves can be intermixed. For example, if the clearance is a 0.5 too large, a 1/1000th oversized bearing can be installed in the top half with a standard insert installed in the crankshaft cap. However, the oversized insert half must be installed on the top of the crankshaft. Now let's discuss rod bearings. Engines are built with two different rod bearing sizes, standard and 1/1000th of an inch oversize. It is not unlikely to have two different size rod bearing inserts in the same engine. As with bearings, pistons can be several different sizes. This is done so a near perfect clearance is established between the piston and the bore. Always reinstall pistons in the same cylinder they came out of. Always remember to mark pistons and connecting rods when removing them. Always install the pistons with the notch facing the front of the engine. Pistons are built with the piston pin slightly offset. This design greatly reduces wear when the piston is moving down on the compression stroke. The 3-liter and 3.8-liter engines have the same bore size. However, because of its longer stroke, the 3.8-liter engine uses dished pistons to reduce compression. If the 3-liter pistons are installed in the 3.8-liter engine, the resulting higher compression ratio could cause pre-ignition, detonation, and possible engine damage. If the 3.8-liter pistons are installed in the 3-liter engine, the lower compression ratio will cause reduced performance. When a new engine is broken in, each camshaft lobe and conventional hydraulic lifter bottom will wear into each other. During disassembly, lifters should be numbered. When an engine is being reassembled, conventional hydraulic lifters should go back into the same lifter bores they came out of. Conventional lifters should never be reused with another camshaft. If a new camshaft is installed in an engine, all lifters should be replaced at the same time. Roller lifters, however, can be reused if they are not damaged. The most critical time for camshaft lobes and lifters are the first few minutes a newly rebuilt engine is run. When rebuilding an engine, coat the camshaft lobes and lifter bottoms, or roller, with a good quality molybdenum disulfide grease to protect them during the first few minutes of operation. Also, as soon as a rebuilt engine is started, run it approximately 1500 RPM for the first few minutes. This is done to seat in the camshaft and lifter surfaces. When reassembling an engine, push rods should be used with the same lifters and rocker arms that they came out of the engine with. Some technicians use a special tray or punch holes in a cardboard box to keep push rods in order. Many technicians wrap lifters with tape and then number them. Also, on the traditional design V6, be sure rocker arms are in the same position on the rocker arm shaft as they were previously. With the new generation V6, be sure each rocker arm is used in the same position and with the same pivot block. When rebuilding any style of V6 engine used by Buick, the oil pump should be primed by packing the space between the gears or rotor with Vaseline. This will give the pump the extra suction needed to immediately start pumping oil. Now that we've reviewed engine changes and rebuilding tips, let's cover the Turbocharger intercooler. To better understand how an intercooler works, let's quickly review engine breathing and turbocharger basics. As the piston moves down on the intake stroke, it creates a low pressure area in the cylinder. Atmospheric pressure then pushes air-fuel mixture into the cylinder. Engines that rely only on atmospheric pressure and on the piston moving down in the cylinder to draw in the air-fuel mixture are referred to as naturally aspirated engines. These engines will produce more power when it is cold or raining because colder air is denser. The denser the air charge, the better the volumetric efficiency. Even the very best naturally aspirated engines have only an 80% volumetric efficiency. That means that a cylinder with a volume of 1 liter will have at best an 800 milliliter charge of air, or 80% of its volume. Engines other than naturally aspirated are referred to as supercharged or turbocharged. This means that an air pump or air compressor is used to force the air-fuel mixture into the cylinders by pressurizing the intake manifold. This pressure is referred to as boost. Supercharged and turbocharged engines can have a volumetric efficiency greater than 100%. Superchargers are slightly different than turbochargers. A supercharged engine uses a toothed belt, a chain, or gears driven by the engine to rotate the air pump. While increasing horsepower, superchargers also tend to make a car less fuel efficient. Some of the extra horsepower developed in the engine is used to turn the supercharger. As engine RPM goes up, it takes more and more fuel and horsepower to drive the supercharger. On the other hand, turbochargers use exhaust gases to power the air pump. Since the energy in exhaust gases is normally wasted once it leaves the engine, turbochargers do not rob the engine of horsepower. Also, by using a turbocharger, a smaller, lighter, more fuel-efficient engine will produce the same horsepower or even more horsepower than a much larger one. A turbocharger is basically just two fan blades connected by a common shaft. The fan blade, rotated by the hot, expanding exhaust gases, is called the turbine wheel. The fan blade that draws in air and compresses the air-fuel mixture is called the compressor wheel. Both wheels are totally enclosed in their own housing that directs the incoming and outgoing hot gases or air. Hot, expanding exhaust gases from the engine push against the turbine wheel, causing both fan blades and the common shaft to rotate at once. The compressor wheel then draws in air and forces the air-fuel mixture into the engine cylinders. If a turbocharger on a gasoline engine was unrestricted, it could force too much air-fuel mixture into the cylinders and possibly cause internal engine damage. Therefore, the amount of boost is always limited to a preset amount. This is done by opening a valve called the wastegate and allowing some of the exhaust gases to bypass the turbine wheel. The wastegate opens when intake manifold pressure reaches maximum boost. A device called an actuator opens the wastegate through a linkage system. On later model Buick engines, the wastegate actuator is controlled by the ECM. There are 5 main parts that make up a turbocharger. They are the center housing and rotating assembly, turbine housing, elbow assembly, which includes the wastegate, wastegate actuator assembly, and compressor housing. If turbochargers are given proper maintenance, they will give many years of trouble-free service. Because of the high speeds and temperatures they operate at, factory maintenance schedules should be strictly followed. You can find information on oil and also oil change guidelines in the Buick Know-How Reference Manual number 84. Remember, Buick's oil change guidelines are for cars used under normal driving conditions. If a car is driven hard on a regular basis, Buick recommends changing the engine oil and filter more often. Engine oil not only lubricates, but it also cools the turbocharger. If a car is run hard, it must be allowed to idle at least 1 minute before turning off the engine. A turbocharger continues to rotate at high speeds after the engine has been shut off. Letting the car idle before shutting off the engine will permit engine oil to cool the turbocharger and allow the rotating parts to slow down. If the turbocharger is not allowed to cool, the engine oil around the bearings and in the oil passages may decompose into a sludge. This process is called coking. In severe cases, the sludge-like deposits may coat the bearings and partially block the turbocharger oil passages. This, in turn, could cause turbocharger bearing failure. Turbochargers can be made even more effective by using an intercooler. Use of an intercooler on the 3.8-liter turbocharged V6 increases performance on an already outstanding engine. An intercooler removes heat from the incoming air after it leaves the turbocharger. This causes denser, cooler air to enter the intake manifold. The denser air-fuel mixture produces more expanding gases when it burns, and therefore more horsepower. Since the mixture is cooler, there is also less chance of pre-ignition. Intake air is drawn through the air cleaner assembly and then compressed by the turbocharger. When air is compressed, it becomes heated and expands. This heated air is then routed into the core of the intercooler. Outside air then passes through the intercooler to lower the temperature of the inlet air in the core of the intercooler. The cooler, denser air is then sent to the intake manifold. A fan mounted on the engine harmonic balancer helps draw air across the intercooler when the car is traveling at low speeds. More information on diagnosing and servicing Buick engines, turbochargers, and intercoolers can be found in the reference manual included in this know-how.